Okay. So since I hit recording late and I don't even know if it's actively doing it. Okay, I hope it is, fingers crossed. So far I just wrote down the kinematic equations and now I'm going through vector addition and decomposition. So for vector addition, decomposition, thank you. You could either just use Sokodoa and maybe have a picture of the triangle if you want and have this like be O. Oh, nope, I drew them in the wrong order. Adjacent, opposite, and hypotenuse. And then you could also put that h squared would be adjacent squared plus opposite squared, or you could put it the way that it was written on your equation sheet last time, which kind of had that one triangle described in terms of V, and then there was like Vx and Vy. Either way, it gets you the same thing. And then I'd probably, if it's something you struggle with, just make a note that vectors add component-wise. And then that would give you your formulas for relative velocity as well, because it's really just a vector addition that's taking place there. From here, we're going to have forces, which you really, most important, you just need to have F net equals MA. It's important that you realize and understand that that F net equation is a vector sum. So if you want to, you can maybe put that as F net X equals M times AX, just so that you have that reminder there for yourself. And then any other force equations that you want. So I feel like FG equals MG might be one that you feel like you don't want to waste the space on, but that's one of the ones we have. The force of static or kinetic friction is just the coefficient of that friction times normal force. Now you guys know Hooke's law. You could put that one over here. So F is minus K delta X. And then the global gravity equation as well. So big G M1 M2 over R squared. For some of these, if you find yourself having trouble remembering certain concepts, like for FS, the main conceptual thing that comes across in that equation is that negative sign tells us that the force opposes the stretch or the compression of the spring. So if you need something like a picture to kind of just have that sink in and really be there, that wouldn't be a bad idea. I can. So well, I guess the variables, example M equals blank. I'm not going to be going through that. I'm just going to go over the equations themselves and the ones that you want to have on here. So I'm not going to be going through any example problems in this session. But I want to get at that if any of these equations, when you look at them, they don't make sense to you right off the bat, or you don't remember exactly what situation they're describing, having a picture could be helpful. And in particular, I'm also thinking about the big gravity equation, like understanding that that R is from center to center distance of your two masses. Because a lot of the times, right, they'll give you like you're on the surface of the Earth, but you're some height above it. Then your R is going to be the radius from the Earth to get from the center to the surface, plus that distance that you would get from the surface to wherever the satellite is, or something like that. The other thing, so maybe I'll just make a note of this in a different color, because there's a couple other things for forces. So diagrams of what you need. And I think that could include global gravity could include springs. Having like a nice solid inclined plane free body diagram pre-drawn might be a nice thing to have on hand if those stress you out. And shoot, what was another one I was thinking of? I don't know. It'll come back to me. These are just examples. You guys customize for what you feel like you need. After you guys went through forces, you'll need to have centripetal acceleration. A global gravity diagram would be something where, say, if I have that this is my M1 and this is my M2, that you're drawing basically that the R is this distance. And just kind of keeping in mind that it's going to be going from center to center and not from, say, surface to surface. So just understanding what that R is in the context of the problem. I'm going to take a sip of my coffee and stop talking so fast. And I will give you guys a chance to ask questions. I just want to kind of give my general rundown and advice of what you absolutely need to have. And then we can get into specific questions you guys have. So I'm going to add a new page and put on continue on. You would then have centripetal acceleration. I'll abbreviate. So AC is V squared over R. This is another one that might be a good one. I'll be sure to save all the slides as photos when I'm done. Or somebody remind me before I exit out, actually, because I might forget. But hopefully I won't. So this might be another one that might be a good idea to have a picture drawn of just like what the direction of V is and the direction of AC. And since you're able to put everything on here that you want, you could also write down some of the key concepts, right? So for AC, this is always going to point towards the center. And then we typically call towards the center positive and away from the center negative. So that's like something else that you could put on. Towards center plus, away from center is a negative, so on and so forth. I think that's what you guys all got to so far for that. We'll come back to some of the optional big G equations from that chapter in just a second, and then because they're not essential, but they're nice, and I think you should have them if you can write them down. But otherwise, we just have energies. So the work equation is one that I would, so choose the form that you like best. So I presented to you guys in discussion, you can either do F parallel times D, or you can do the FD cosine theta. This would be one that I would probably say you should have a picture showing D and F and the theta that we mean. So that has to be the angle between F and D. Otherwise, our conservation of energy law is basically that our E initial total, so all forms of energy total that we're starting with, plus any net external work that's going into the system, is going to be equal to all the forms of energy we have at the end total. And then all those different totals can be made up of our two different types of potential energy or our kinetic energy, which would be our PEG is mgh, PE spring is 1/2 K delta X squared, and kinetic energy is 1/2 mv squared. And then you guys have been introduced to power. So power is work divided by time. They sometimes also will give you that average power could be equal to force times average velocity. This again would be a dot product. So same rules apply as for work. And I think that's it. And I don't think it's as important here, but the key for the energy parts is going to be the conservation of energy. So if you need to, again, have maybe like a little picture of like that roller coaster thing that I drew or some other energy system. When I say dot product, that's a good point. So when we're multiplying in the work, the force times the distance without the angle or anything, that's written as F dot D. Because it's vectors multiplying each other, it's a special type of multiplication that they just call the dot product, and they use a dot to represent it. But it just means that we're taking the parallel component, or we're doing that magnitude times cosine theta. So that would also be the same thing as either of those guys. So yeah, I think that's everything that you absolutely need to have. I'd say the other kind of optional ones I can think of for especially the global gravity would be the Kepler's law. So I guess global gravity / orbits. And that is the T squared is 4 pi squared r cubed over g times m. And then I know that there's another one for velocity that I know you guys have, and I can't remember what it is off the top of my head. But the other one I'm thinking of is for finding the global gravity like on a new planet. So sometimes they just call it little ag for like gravitational acceleration on somewhere else. That would be g mass of that planet divided by the radius squared. So I think there might be one other one. Having those on there might be nice. But yeah, I'd say if you're running out of space, for me, those ones are optional, but I think that I would probably recommend that everyone just put them down. Okay, and I'm going to go ahead and save these screens to my photos, and I'll post them along with the recording. And otherwise, I guess I'll open the floor to questions. I'll leave this, I just keep adding. I'll leave this open for now.
Would you be able to explain like when R is capital versus lowercase for
It doesn't really matter. I guess they typically will do that if you're dealing with like the radius of a planet, just because it's usually a really large number. So they'll write it with a capital R just because it's so big.
Okay.
But it's so, yeah, so it does represent the same thing in the other equation that I wrote and in these ones as well. So these might be other ones that like, again, you kind of draw, you know, some planet with like, if this is the orbit, this is the distance r. It's from the center of whatever you're orbiting around to, it's just your radius, essentially.
Okay, thank you.
You're welcome.
So I know she just asked about like big R and little r, but I was working through some of like the examples in the textbook today, and one of them had something about like range.
Yes.
Is there a specific equation for range?
I don't know it off the top of my head, but I know it's in the lecture slides. And I mean, all that I would say, so that one would go with kinematics. So I do think in general, breaking it up by topic and blocking it out that way is just a nice way to like optimize the flow of your page, if that makes sense. And so the range equation would go with kinematics. And then you could also put in parentheses next to that capital R, like this one stands for range, where the other one is going to stand for radius. So you could do that all over the page if you need to. That's not something I hadn't mentioned, but like I kind of did it here for work. I wrote work and then the capital W.
Okay, thank you.
You're welcome. And then to answer Lexi's question in the chat, I would probably say, since it's Tuesday, I'd say try and go through the practice exam. I would prioritize the practice exam and the questions that are in your lecture, honestly. I think I didn't verify this myself, but I'm pretty sure that one of the questions from your exam last time was pulled directly from the slides that he did in class. And that's kind of like one of their justifications for putting something harder on the test, especially if they showed it to you in class. So those would be the two I would focus on, and trying to do the practice exam or those equations from the lectures with only the materials that you would be given on your test. Just to see where your weak spots are and what you do need to be putting on your equation sheet, because it's something that you needed or forgot or something like that.
I have a question about like how to go about finding out which equations to use. So like I feel like when I'm doing problems, the hardest part is knowing which equation to start with.
Mm-hmm.
And I was seeing if you had any like tips or something to help with that.
There are some general keywords that will come up over and over again. So like generally, if you have something having to do with circular motion or something moving in a circle at all, you kind of know like, okay, well, I might be using centripetal acceleration here. I mean, they usually will talk about, like, the only keywords I could think of for forces is they usually will like explicitly say something about forces. Energy and kinematics, I feel like, are going to be the hardest things for you guys to differentiate between, because you can solve most of those problems both ways. But typically the kinematics way is a little bit harder because you'd have to deal with that vector addition stuff instead of using energies, which are scalar quantities. But as far as like the order of the test goes, at least they do, and I think your last exam was the same way. It does go in order of topic. So like your first quarter is probably going to be your kinematics and relative velocity. The next portion is going to be forces. In forces, they usually throw in centripetal acceleration and the gravity stuff, and then energies will be at the very end. But that's kind of the best suggestion I have, other than also if you have your givens and you have your unknowns listed, and kind of first just think about everything that the problem's laying out for you, and then compare with what equations that you have that match what you're given and what you're looking for. That's kind of really the only thing for that. For conceptual questions, I would say review the lectures for that, but reading might be better. I will also say that even though they're classified under conceptual questions, a lot of times the concepts are being represented in the equations. So you could still find the answer you need using the equations, or even just by looking at them. I can't think off the top of my head, and I want to keep this a little bit more focused on the equation sheet. But if there's an example question that you find with a conceptual question, ask in discussion on Thursday, and we could go through it then. Because I know that there's a few on the practice test. For springs, yes. Let's see if there's room on that other page. There's not. Okay, I'll just do it on a separate thing. So for springs, the concept comes up in the equation. So the equation is this negative k del x, which this negative is just telling us that force opposes the change in length. And you can kind of remind yourself of that by drawing a picture if you need to. You can draw like a equilibrium spring first. So this is one where it's just chilling. We're at some equilibrium position. And then if you were to have one that was stretched, so our delta x is going to be pointing downward, our force would be pointing upward on this spring. And same if you were to do a compression instead of a stretch. So we'll compress it like that. So the delta x is pointing upward, but the force of the spring is going to be pointing downward. Okay, so so for multiple choice, as far as like if you can't figure it out, I mean, I think general test taking would say try and eliminate as many answers as you can. So generally there are going to be some answers almost on every question where you have one that's like way too high or way too low. And then just guess if like you're really at like the end of your rope. I'd say generally try and answer the questions that you can first. And if you get stuck on one, just skip it and move on to the next. Like you have a finite amount of time. So you want to spend it where it's going to get you the most points. So try and just do a first pass and save ones for later if you have to. And you should be able to put notes on the equation sheet. So for as far as the guideline said, it was just one sheet front and back. So it's as much as you can fit on there and understand. So yeah, definitely make notes about concepts and things about equations that like don't make sense when you just look at them if you need a little bit more context.
In lecture, somebody asked him if he would upload the like sample equation 2 sheets that he gave us, and he mentioned that he would.
I think there is.
Okay, so I guess then if he's uploading that, so technically we don't really have to write all those equations down, right?
No, you don't
if
have
we're already going to be
to.
given.
Yeah, if you want to use, so I'm looking now, it's under exams in the files. So files, exams, and then exam 2 equations is the PDF. And I just want to glance over it and see what he has. So the whole first page is the exact same as what you guys had on the first exam. And then the second is has all the new stuff. So if you do like that one and everything's there that you absolutely need, you can go ahead and just, well, the only issue I guess is that this is going to be 3 pages and you guys are only technically allowed 2 since you're allowed 1 page front and back. So you might have to rewrite these just so that they could definitely all fit on 2 pages along with notes with like no problem. But I think you are just going to have to rewrite some of them down.
Okay, I just on exam 1, how he made it like a PDF at the top of like the exam page. I just wasn't sure because somebody had mentioned, he was like, "Oh yeah, I can do that," but I just wasn't sure, if he really was going to do that or not.
Okay, yeah. It's
Then that would give us like a lot of extra space then if we wouldn't have to really concern about those that are already given.
Oh, I see. Yeah. So I don't think on the exam you're going to be given anything at all, except for
Okay.
what you have written down. But he just provided one that I guess you could use as a base for yours that has kind of everything essential that you need. And then you could put on anything else.
Okay, perfect. Thank you.
You're welcome. Yes, I can do one for friction because I think that's a common one. Where am I going to do this? I'll do this over here. So if we're doing, so I'll say incline without friction. So our incline is going to be something like this, where this angle is theta. We're going to have normal force pointing perpendicularly to the incline. We're going to have FG. I'm going to draw these kind of big just so I could draw the components. FG is going to be pointing straight down, and then our axis of motion is going to be tilted to be along either parallel or perpendicular to the incline. So we're going to just want to break up that FG into parallel and perpendicular components as well. So I don't know what he called it for you guys, but I'll call it FGY and FGX. And then this angle will be theta here. And then you could also write down FGY equals FG sine theta. FGX equals FG cosine theta. And then I don't think I can copy and paste, but the only difference for with friction, so I'll then put in red, with friction, if there's no other forces acting on it at all, then friction is going to be opposing the downward motion and will be pointing up like this. And I guess
Hey, Corinne, maybe I'm terrible at trig, but is FGY actually supposed to be cosine?
Yes, it is. Thank you.
Okay, cool.
That should, oh my God, I'm going to rewrite the same thing. Nope, we want cosine and sine. Yes. And then I was just deciding this could be static or kinetic for that frictional force. But yeah, everything else stays the same.
Is it possible for you to show an example of what a, like, I guess it's a free body diagram for centripetal force?
Yeah. So I guess it would depend a little bit on which one. Yes, those two angles would be equal. So I guess if you were to do one like vertical circle, I mean, you could always label them, right? So that's just what I'll do. So if you have one like the vertical circle that we did in class, and this is our center, this is our orbit, then we would be looking at the top and at the bottom. At the top, we would have force, tension, force, gravity. At the bottom, we would now have tension pointing up and FG pointing down, and then I guess in blue, just throw on that AC in both of those cases would be pointing towards the center. And then you could also, for comparison, I guess it would probably be like a Ferris wheel, you could call it. But for a Ferris wheel, you would have a very similar, I mean, it's just circular motion, right? So we're going around in our circle. But at the top, now if we're thinking about sitting in the seat, we're going to have F normal pointing up, FG pointing down. And that would also still be F normal. And FG, and our AC is still pointing towards the center.
Okay, so the only difference in those is that one of them's dealing with like tension of a string and one of them's dealing with just like an object on the top of a Ferris wheel.
Yep.
Awesome, thank you.
Oh, yeah. Okay. This is a good question. This is a harsh question for me. So I will say, I don't quote me on it, but it would be very, very rude to be asked a banked curve question on a test. However, test 2 is traditionally the hardest test that you guys get all year. So maybe. So I'll draw that one out too. So let's look at banked curves. So this will be a similar picture to the inclined plane, but now, and I will just kind of do a box. But now we're thinking about our acceleration pointing not along the tilted axis, but moving along the circular axis. So this is kind of the side view of the circle. And then I'll just draw the forces in blue. So we have F normal, FG, and let's see. Yeah, and I think friction would be going this way. But now instead of breaking things up into perpendicular and parallel, we're going to go back to breaking them up into just our traditional X and Y. So now we're going to have a normal force. Oh, I wanted to do this in red. So we want to break up normal force to go have an X component and a Y component. And same with friction. So FSX and FSY. And then from both of these, this angle would be the same theta as the angle that's on the of the incline or of the banked curve. But I would, and there should also be these pictures in the book as well, just in case I don't get to your question or you think of one later that you're like, oh shit, I should ask her in this. Just try looking through the book or looking through the lectures to find a good, clear example of somebody else who's drawn it, and then just copy the one that you know is right. I mean, make sure that you understand it before you just copy it, but take the time to really examine one that you know is going to be right and then redraw the correct version.
Are there any like free body diagrams or anything that we should know for like kinetic energy or power or like stuff like that?
The only thing that I could really think of for kinetic energy is if for some reason, maybe having an example of what is meant by using the conservation of energy equation. So I'll put this on a new page as well. So if you were to have, say, the EI total plus work net is your EF total, or however you end up writing it out, maybe having some sort of picture of even like just something going off a hill. And you could say like there's gravitational potential here and kinetic energy here if there's nothing else. And if this is 0.1 and 0.2, you would say that the E total at 1 equals the E total at 2. And that would just be the gravitational potential equals the kinetic energy. But otherwise, I can't really think of anything off the top of my head that you would absolutely need to draw a picture for the energies. I think the forces are typically the ones that are a little bit more hairy. Okay, does anybody else have any questions?
For the like projectile motion stuff, is that just under like the kinematics equations?
Yeah, that's when I would put with kinematics. And now, actually, so now that you do have the opportunity to draw and write your own equation sheet, now I wouldn't say it would be the worst thing in the world to write down the range equation that he gave you and some of those kind of specialized ones, as long as you kind of draw that this is the situation. And then you could put all the things that, you know, if that's max height, then this is the range. And like you could kind of put all the things on there that need to be true in order to use that one. But yeah, projectile motion, I just kind of threw under kinematics because it's the same equations.
Okay, thank you.
I'm always confused about when to use the work energy principle versus like the work energy principle for non-conservative forces. And then like the conservation of mechanical energy. Like what can I write down that can help with that? If that makes sense.
Yeah, so the main difference between being able to use the work energy principle and then the one for non-conservative forces is going to be if you have a non-conservative force present. So typically that will be, well, the conservative forces that you guys know of are gravity and spring forces. So those are really the only two that you guys know. And we represent those as potential energies instead of thinking about them as work. So I'd say if there's any other forces present, then that's a non-conservative force and you want to use the non-conservative one. That being said, I'm also not completely the biggest fan of the work energy theorem. It comes out of if you were to use just the conservation of energy equation itself. So I actually have it written up here. So like if you have potential energy initial plus kinetic energy initial plus W net, which that W net would be something from a non-conservative force, equals PE final plus KE initial. Nope, KE final. Oh my gosh, what am I saying? Then you do have something on your equation sheet, I think, that rewrites this then as if you subtract and get the kinetic energies together and the potential energies together, then your W net is going to be equal to final minus initial potential. So we can write that as the change in potential energy plus the change in kinetic energy. And then depending on those special cases, and yes, I did say spring and gravitational forces are conservative, and which is why we usually write them as potential energies. We don't put into the energy equations work due to gravity. We just put in the potential energy due to gravity. But yeah, so if you have this, rework this equation in this way, then depending on if you have conservative versus non-conservative forces, you'll end up back to the work energy theorem with just F net equals delta K, or if you need to have the potential energies in there. And Howitzer is outside on the deck. I can bring him in at the very end. We can have him sign us off. I believe, yeah, this would be the non-conservative equation, since the work is accounting for the potential energy and the kinetic energy. Yes, please show me Nash. Alrighty, any more questions? I should have that video up. So I didn't include power in the work and energy video that I did. I'm going to edit and upload it tonight, just because you guys don't really get into power too much. Those are typically really just plug and chugs for the most part. So you're either getting work over time after you've used like energies to find work, or you're doing force times velocity. So just based on what I thought was the most important before getting to the test, I focused more so on doing work and energy stuff than including the power. But yeah, that should be up tonight. I just finished editing the new pulleys video, because apparently I was very confusing, and I'm so sorry about that. Looking back on it, I was like, yeah, I don't know why I chose to approach this way. So that should be clear and up tonight as well. And then I filmed a Hooke's Law video. So those 3 should be up by tonight, and I'll post that along with this stuff on the announcements. But yeah, I guess if I'll save the rest of these, so I don't need to save those 2, but I'll save those. And I guess if no one has any other questions, I can go find the puppy. Okay. Then let me stop my video and I will go downstairs. bouncer. Come here. Oh, get over here. Here. Here, let's get treats.
Yeah, Lexi, I can text you all like the stuff I have written down.
Such a brat. I'm gonna give him Doritos to sit. Can you sit? Will you paw? Oh, what a good boy you are. You want it? No, you're done with this. Ah! Alrighty. Oh my God, he's so cute! We got a corgi. We got 2 corgis. Oh! Okay. Thank you guys so much. Yeah, and I'll post those for you too, Lexi, in case you can't get them from somebody else. But I will see you guys on Thursday, and good luck studying. Bye, guys.
Thank you.